So, good afternoon, and thank you for inviting me to present here essentially some thoughts that I would like to transmit, and actually I should dedicate to the memory of John Aitchison, who used to insist on the role and the importance of the sample space. Sorry, my voice is not the best today. What do we know about the sample space? When we make an experiment, we obtain some results, and we express these results as data. Data can be of different types: categorical, numerical, functional, sets, whatsoever. But they are observed and recorded in a sample space, and it is important to give some thought about which is the sample space of our data. What we expect of our sample space is that it includes at least all possible results. This is the minimum. We expect, or we may or not attain the border values. Infinity, when we have the real space as sample space, is usually not attainable. But it can be included in the sample space. Which are desirable properties? Desirable because they make the analysis easier, more accessible. That it not only contains all possible results, but it has a structure. And we will see immediately why the structure is important. The structure should include a scale. How do we measure differences? In the previous talk, we heard about comparing two groups. Comparing means making some kind of difference. How do we compare the groups? We can be interested and are usually using operations. We use the sum, we use the product, we make a shift, we center the data, this is a shift, and we don't think about it. We consider this to be the natural way to operate with the data. But we should be aware that this is not obvious, always so natural or obvious. The typical real examples that we have are real space, the positive ordinate of real space. We just heard about the simplex, the hypercube, the hypersphere, and others. Why is the sample space so important? Just two elementary examples. There are many more, but these are well known. Consider the mean and the variance of a random variable. How is the mean, are they defined? Consider the variability with respect to an arbitrary point, A, and then the variability is the expected value, usually of the difference here, the square difference between the random variable and the fixed point A. The mean is then defined as that value A that minimizes this expected value. And this is called here mu. And then the variance is precisely this minimum value. Okay, but here we have some underlying assumptions. It is not an abstract concept that holds like that. We are assuming that X is a real random variable, that the sample space is R, and that it has the usual Euclidean geometry we learn in school. This is something we take so for given that nobody thinks about it. Nobody is not true. Fréchet, at least, in 1948, he already defined a general way to define variability, variance, and mean in general metric spaces, not Euclidean spaces. So he substituted this squared difference by this squared distance. And this makes a difference. It's more general. Then the mean is that value that makes this minimum. Here there should be an A, it's a typo. And the variance is this minimum value. Okay, so we built a lot on this idea of using concepts that hold in Euclidean spaces, but are not necessarily the standard. The assumption that the real space is the sample space. Let's go to compositional data. In compositional data, which is our definition of compositional data? Not only closed data, close to a constant sum. We consider data that are strictly positive and carry relative information. So any point here in the positive ordinate of real space can be a compositional datum. If they carry relative information, it doesn't matter where it is located. All the points on one line going through the origin will carry the same relative information. So we can consider them to be equivalence classes. Every line through the origin will give us an equivalence class. And from mathematics we know that if we work in equivalence classes, we can take a representative of that class, of each class, and whichever is proven for this representative will hold for the whole class. So we take the simplex that was mentioned in the talk before as a representation of those equivalence classes, and we can take the closed representation with constant sum as a representation, but it's not the only one. The properties of compositional data hold for the whole real line, for all the equivalence classes, and thus for each representation. There are situations which are not closed. When we consider molar concentrations, they don't sum to a constant. In practice, the simplex is a subset of the positive ordinate of real space, which is itself a subset of real space, the dimensional real space. The constant to which the data are closed is frequently 1 or 100 parts per unit, probabilities also, or proportions, percentages, but we require the scale invariance for those, for all the properties, so that it holds. So our definition, positive data, strictly positive data that carry relative information. This includes not only data in parts per unit, in percentages, or other constant sum constraint data, but also molar concentration, relative abundances, whichever you like. Relative information is the important point. So for us, the total is completely irrelevant, or in general non-informative, although I will mention briefly methods to deal with informative totals. But our interest lies especially in relative information. And the principles that underlie our approach here is scale invariance. So scaling factors do not alter the results or the analysis. And subcompositional coherence. And this is important. What is a subcomposition? A subcomposition is simply, in practice, taking only some parts, some components of the vector, and taking a representative of that. You can reclose it to use the same representation. And then to require that the analysis is coherent. What does that mean? In particular, very important, the dominance of distances. The distances between two compositions in the larger composition should be larger or equal than in the small composition, something that frequently does not hold. To understand the idea is easy. Consider 2 points in space. They have a distance. If you project them on the table, the distance will be shorter in general, equal if they were in a position parallel to the table. And this is something that holds in space for the Euclidean distance, and that we expect to hold as well for compositional data. So this is one important point, scale invariance for the subcomposition as well, and that the ratios of common parts are preserved. So that they don't, changing the scale, changing to parts per unit, from parts per unit to 100% does not change the results. Here are some examples of which is the relationship. Consider here these equivalence classes. You have proportions here on this segment, and they can come from many possible situations, like the red points projected are the same as the projections of the blue points, the same as the projections of the green points, the same as the projections of these violet ones, which are erratic. So many situations can generate the same proportions or parts per unit. So this means that if we don't know the absolute values, there is no information available on how the absolute values could have been. It could be any situation. Here you have one proportion and many possible origins or absolute abundances that generate this proportion. So a large variability leads to a simple point in the representation. So, which are the problems? The problems are that standard methods are essentially based, in most cases, in the immense absolute majority of cases, on the assumption that the sample space is the real space, and that the Euclidean geometry holds, and that the Lebesgue measure applies. And with compositional data, with frequencies, the sample space of frequencies of relative data is not the whole real space. They lead frequently to nonsensical results. The most frequent examples that have been seen in the literature are reverse of the Euclidean distance between observations. So they change, but they don't change in a controlled manner. They are not getting all larger. Some are getting larger, some are getting smaller. It's kind of at random. Correlations in a bigger space or for a subcomposition and for a big composition are not coherent, they are spurious. The covariance matrices are not only spurious, they are necessarily singular. So all methods, absolutely all methods based on the covariance matrix can lead to nonsensical results, to results that are in contradiction from one composition to a subcomposition or with reality. And popular methods in the microbiome field, like the Bray-Cortis dissimilarity or the unifrac distances, weighted and unweighted, have problems as well. They are a scale invariant, but not subcompositionally coherent. It's quite easy to find examples. So be careful with these points. Here is an example. It's a toy example adapted from a presentation from John Aitchison to illustrate the problems with closed data. Consider here 3 samples. We have 2 scientists. Scientist A records animal, vegetable, mineral, and water parts in 3 samples. Scientist B records the same except for the water. So the samples are aliquots, so exactly identical to simplify the situation. And in this case, what we have is A records 4 parts, B records 3 parts, and they are exactly the same, only that B doesn't record this and recloses the sample. If you compute correlations in this context, and if you have closed data, you can play around. It happens always that situations like this appear. First of all, you will see negative correlations. This can be shown mathematically to be so always. It's called the negative bias of correlations in proportions. And then you can get nonsensical results. Look at this 0.5 correlation between 1 and 2. Look at this minus 0.5 between part 1 and part 2. So A says when the animal part increases, the vegetable too as well. And B says, no, that's not true. It's exactly the contrary. And if you imagine this in practical situations, it can be really a debate. So I hope that in the meanwhile it's clear that the sample space is more than a set. It's not just a set of numbers. It's a set of numbers with a certain structure. And if we want to compute distances, if we want to compute expectations or variances, we need to know if the structure we are assuming fits the sample space and thus the problem we are looking for. So based on early developments by John Aitchison, it was possible to prove that the simplex, as a representant of the equivalence classes, is a Euclidean space. An Euclidean space with a group operation called perturbation, with an external multiplication called powering, with this definition, with an inner product, an inner product that we need to define angles, to define orthogonality, and from which we can derive a norm, the length of a vector, and a distance between two vectors. For instance, a distance between the mean of two populations. We term this Aitchison geometry. It is an Euclidean type geometry. So the same properties that we can recognize in the Euclidean geometry of real space, we can find them in the Aitchison geometry in the simplex. So the reason to call it Aitchison geometry was twofold. One, because it was based on early definitions by John Aitchison. The second was to make clear that it is not the standard geometry that we are used to apply to our data. Which properties does such a geometry have? It allows to define Cartesian coordinates. We call them ILR, isometric log ratio coordinates, and we will see immediately some examples of such coordinates called balances, which are, let's say, simpler coordinates. We have operations and metrics, and we know that if we work on a representant of the equivalence classes, then this representation in coordinates will give us values that are in real space and for which the Euclidean geometry in real space holds. So we can work on coordinates and apply all the standard methods to those coordinates. So we are back to the known methodologies, which is quite good in the sense that all the available tools can be applied. Which are the difficulties? Correlation in terms of parts of the original components of a composition does not work for compositional components. We need alternatives, and we will see tomorrow some search for alternatives based on proportionality. Questions formulated towards the data, the questions that we want to analyze. It would be better to formulate them in terms of ratios, because in terms of ratios, we can answer them. Questions or statements about single parts is, in our opinion, nonsensical. Because if we know one part, we know all the amount or the proportion of the other parts that are not this thing. If we know one property, we know what it is not the other property. So we always have more information than one part. Not taking into account this fact is discarding information which can be important. So, how do we look at this? When we have proportions, we see things like this. It's possible to prove that this here and this here are orthogonal axes. They don't look like this, but mathematically they are. This here is an ellipse. This here is in another ellipse. they don't look like this, but this is the type of data that you are analyzing when you analyze the raw relative data. So it's not a surprise that many things don't fit. If you represent them in coordinates, you will see something like this. One ellipse, the other ellipse, the axis of the ellipses, which are orthogonal. So working in coordinates allows to see what we expect to see. Working in proportions can be very difficult. And here a way to build coordinates which are based simply here. There are 11 taxa, and we perform a sequential binary partition. So we first take the 11 taxa and divide into two groups, 7, 1, and 6, and the rest here. Then we divide this group here in two groups, 7 from the other two, and then 1 from 6. And the same here, two groups here, and then each group, and each step again in two groups until we cannot divide anymore. This defines coordinates, Cartesian coordinates. We can show that they are Cartesian, and the formula to calculate the coordinates, the values of each sample on those coordinates is given here. There is a group of samples in the numerator, here in the denominator, the natural logarithm, and this is a normalizing coefficient, so that we obtain orthonormal coordinates. So with unit length. Yeah? This is an interesting comment. It can be chosen in a blind way. But usually it's much better to choose it using expert knowledge, and there are probably presentations tomorrow about using a phylogenetic tree to do that. Or you can do some other criteria, like we have a method to find principal balances, what we call. These coordinates are called balances because it's an equilibrium between those groups of parts. These principal balances aim to approximate principal components. So, nevertheless, for interpretation, it's clearly better to have some expert information like the phylogenetic tree. But what we can assure from a mathematical point is that these coordinates will be Cartesian coordinates, so orthogonal coordinates, and you can apply standard methods without the risk of getting spurious correlation or things like this. Here in this case, we have represented 3 different groups of samples. These 3 groups here, and you can see here these bars are located at the center of the group. Imagine we have this representation of the sample. We can compute all the values of all the samples in each balance, and then for each balance we can compute the sample within each group of the 3 groups. And here we have a comparison of where those means are located, and we see that the green group is more to the right, so this means that this group of taxa weights more in this group than this, because they are pushing to the right. The variability, which is proportional to the length of the bar, is larger in this group than in the red and the blue one, and so on. So we could say that probably these three groups are very different, and you can perform a standard test on equality of the groups or not. So just a few comments about other sample spaces. This is the standard approach, the raw approach. We have obviously the Euclidean geometry and the Lebesgue measure in real space. The problem is Euclidean distance is not subcompositionally coherent, it is not dominant. Information is considered to be absolute, not relative. It induces spurious correlation. So, to take into account the constraints of compositional data, that they are positive, that they are not larger than a certain threshold, that they have a constant sum constraint, you need very complex models that don't account for the strange figures that we see in relative proportions. Another frequent approach is the logarithmic approach. It is usually considered to be directly as a subset of the real space with the induced measure and geometry. So it is confusing how to deal with the patterns that we observe, but it is based on two key elements: relative information, the same as with compositional data, and the total is assumed to be informative. In such a case, what we consider as a possibility that can be interesting, especially to explore the relative information or the compositional information in the data, is to use a T-space, which is a product space of the positive real line corresponding to the total, to the informative total, which can be modeled then, and the information contained in the composition. And this allows you to work in this space. And then Aitchison's log ratio approach, which had this implicit vector space structure, and he introduced these two transformations. We have heard about the second, the ALR, in the previous talk, which is a log ratio with respect to a fixed or reference component, or the CLR that was mentioned in the debate, which is the log ratio of every component about the geometric mean. They give the false impression that they are easy to interpret because you have here only one part, and there are, at least with the CLR, there are as many components as in the original composition. But it is not information about that part in an absolute sense. It is information about that part, about the geometric mean of all the parts, including the part in the denominator, in the numerator. And this makes it confusing. The problem with the ALR is, apart from interpretation that you have always a log ratio, is that it has is associated to an oblique basis in the Aitchison geometry, and this has additional difficulties because working in an oblique basis makes it more difficult to deal with distances, etc. I think this is one of the reasons why in the UNCOM approach you need so many tests to look for all the possible ratios, because not all methods are permutation invariant. So, by the way, the ALR is known as the softmax information, according to our information. And this is the essential part of the talk. I would like to insist, don't forget the sample space when you have data. Analyze which is the sample space, which is the reasonable structure. Are the methods you're going to apply designed for that sample space, compatible with the operations in that sample space? It is important. It is important to have a clearly defined set. The measure of difference, how we measure the distance, is essential. The algebraic geometric structure is very helpful to design methods, to design an approach. The debate can frequently be reduced to a debate about between the sample spaces underlying the different methods. So it's not necessarily a difference between the methods themselves, but how or where they are applied, which is the sample space, the underlying assumption. And the last comment is, for compositional data, it is advisable to think in terms of ratios, which is not always easy, but it is something that can be helpful in itself. So, and here are some references, and this is an invitation to CODA Work 2019. Thank you very much.
Do we have any questions?
You were talking about the sample space and its importance, but what my understanding is that the raw sample space that we're talking about is sequences, short sequences. So how does that fit in?
I think that sequences have the problem, as far as I know. I'm not an expert in microbiome sampling, but the total, it depends more on the machine and the size of the sample than being informative itself. So what you have really is relative abundances. And as soon as you have relative abundances, you are in a simplex sample space.
So like sequences that are close to each other in terms of the, one change. They might be counted together, or so there is something fundamental about that.
Yeah, but this is related to the sampling approach, not to the concept of the sample space. Maybe there is a confusion. When I talk about the sample space, I talk about the space where you reflect your results, not about the way of sampling, which depend on the machine and on the specific samples you take. And there are certainly issues that differ from field to field. The problem in microbiome with sequences is different from the analysis of geochemistry, or from the collection of samples in economy, where you have as well compositional data.
I really like this question because I think it's sort of crucial, is that the observed data is it's a series of sequences that have nucleotide information. We just happen to typically summarize that, actually usually through a whole nother model, removing a lot of that information, collapsing it to counts, which again, counts also are not necessarily, don't have the same sample space. I think, you know, I apologize, this is less of a question and more of an opinion, but you know, the counts themselves seem to have relative information. I think that the ongoing problem is how do we move farther and farther upstream and actually deal with more of the variation that we're ignoring, that's present in the data, but we don't know how to deal with yet.
Another opinion. I think that, yeah, they are counts. You know, when we get an OTU table, they're integers. And I think that there's a fruitful ongoing discussion about, you know, how do you take the log of 0 when we do log ratios and these analyses. And one option is you can replace 0 with a pseudo count of some kind, justified by some method or another, and raw transform your data and use these compositional tools. Another option is, say we wanted to assume the counts were Poisson. Now, there's still the conceptual issue of the nonsensicality of making a statement about a single species, when we know that the total number of sequences counted for that species could depend on the number of samples on that illumina lane and other things that are somewhat irrelevant to the biological process at hand. But if we did some multinomial regression or something like that, we're doing regression on a log of a probability, so the canonical parameters, or the parameters of the multinomial, do fall on the simplex. The canonical parameter for that is a log of a relative abundance, and we can still do these sorts of CLR-based analyses of that relative abundance underlying a multinomial, and I think we'll hear more about that over the course of tomorrow. Yeah.
Yeah, thank you for, I mean, you know much better than I the problems with sequencing and sampling in microbiome data.
Absolutely, and I think there is there's two steps in any kind of compositional data analysis, even if we're working with mass spec data or something like that. At the first step, we have to define some kind of atomic unit that allows us to count things. Otherwise, we just have zeros and ones. You know, this is the particle that hit the window or hit the shield, the however you call it, the sensor at exactly this time at exactly this place, and everything is either 0 or 1. But we say, okay, well, that particle is a similar mass, and so we're going to group together particles with a similar mass, call them a compound or a molecule, and then we have the counts of different molecules. So there's this first step of defining our atomic units, and there's been some ongoing research in that in the microbiome world about do we denoise our sequences to say, well, okay, there's really this one sequence, and then there's sequencing error cloud about that. Do we group things with some sequence similarity threshold? But yeah, there's this first primary step of defining these fundamental units and aggregating them together by counting. And then after that, there's a branch in whether we continue on with account analysis and multinomial models and stuff like that, or if we want to figure out how to take the log of 0 and do these more compositional analyses.
I have a question. So there are some pretty bold statements made here about correlation and this type of inference that that appear to be wrong. It makes me wonder, at least, what sort of inference we can do. Is there a starting point that you recommend so that we can actually start beginning to play around with these compositional methods?
I'm not sure I understand your question. I mean, when you have compositional data, obviously you can make inferences about the phenomena that are related to proportions or relative behavior among parts. I am convinced that you hardly influence, I mean, I'm thinking about a colleague that is working on finding balances for better predicting some disease. So early detection and similars. And the idea is what we will always see is the relation between two or more components, not the change in one component. So we cannot observe that only one taxa is changed due to a illness or some drug or whatsoever. We will always observe only the change of several, at least two. So why not formulate the question on which are the ratios that are related to our problem? Finding which changes in these ratios will have an impact or a predictive power for the problem we are analyzing. And I think this should be or is the starting point, because with ratios, with log ratios, and we use log ratios because it symmetrizes the problem and it goes into the whole real line, whereas only ratios stay in the positive part of the real line. So with log ratios, you can do correlations. You can do all the standard methods, no limitation. You better take orthogonal coordinates for representing them, because otherwise you will have other types of problems. For instance, making a correlation matrix of an ALR depends on which is the reference part. I would not advise that.
Okay, do we have any more questions? Okay, well, let's thank Vera for giving her thoughts.